Cool. Hello, everyone. Um, Thank you for joining us. Welcome to our beginner-friendly system design series. My name is Alexander, and I will be the host for today's event. Before we get started, I just want to give a brief overview of the series. So the goal of these talks is to help you get started with system design um, on real life app examples. So during each event, we'll talk about how to build a certain app from scratch from the system architecture perspective. So we will not have any coding, just conceptual overview and walkthrough. And also each event is going to have 3 to 5 core app features that we will discuss. So today's event is called How to Build GitHub from Scratch, and we'll talk about introduction to Git and software version control systems, basic features of a Git service, pull requests and code reviews, search capabilities with GitHub, and CI/CD, so continuous integration and deployment pipelines. We'll have a few events in this series. So the next one is going to be next week. So I'll post the details soon. Also, we want today's session to be as interactive as possible. So feel free to drop your questions in the chat and we'll answer them live. But now I want to introduce you to our today's speaker, Lucas, who is a Google developer expert in cloud. So thank you so much for joining us today, and take it away.
Awesome. Thank you so much. Well, hello, everybody. Today we're going to talk about how to build GitHub. I wanted to get started with a little bit of a history lesson. First of all, Git is a version control system, and version control is the practice of controlling files and versions. A version control system is any system that automates that process, and that means the ability to store files, to retrieve different versions of files, to revert to old versions, that sort of thing. So if you've used any system like, let's say, Google Docs, where you edit a document and you can see the history of all the changes and you can go back to the changes that you made previously, that's a form of a version control system. So distributed version control is also something interesting. It's a version control system where everyone who has a copy of the repo has the entire repository with all of the branches and all of the history and all of the code. And having a distributed system versus a centralized system makes it really easy to do things like branching and merging very quickly. It allows people to work offline and in different countries and different time zones. And it makes it easy for there to be many different backup locations for the source code. So there's not just one monolithic server that holds all the code, and when the server's down, the code is unavailable. So version control has been around for a while, longer than I have. The very first version control system was SCCS, developed by IBM in the early 70s. And that was obviously a commercial system that was used by customers of IBM and by IBM themselves. The very first sort of open source, widely accessible version control system was RCS. And that's the very first one I used. RCS was local on your machine. It managed all of the changes on a file-by-file basis. So each file had a version history for that file, but the files were not part of a larger project or repository. In the early 90s, CVS grew in popularity, and this was a client-server model. So I would have the code on my machine, but then I would check it into the server, and there's a CVS server somewhere, and that's where all of the code lives. Also, CVS is when we first got the concept of like a repository where all of the code contained in this thing is all related to the same project. Later in the early 2000s, Subversion grew in popularity. That was an open source project that's now part of the Apache Foundation. And this is when we first got the ability to sort of commit a bunch of changes all at once as a single atomic change. So for example, instead of making changes to the first file and committing those, and then making changes to the second file and committing those, and then having to keep track of which version of those two files you want to be able to deploy in order to get your thing out. Now this sort of repository has a state that represents all the files in it atomically. And there's even version control. So version introduced version control on a directory. So if you renamed a file, then it could maintain the concept that that file had one name earlier and it has a different name now. Whereas before, those would be two completely distinct objects in the system. And then actually, there was another system that I'm not going to talk too much about called BitKeeper that was around the same time as Subversion. And that's what a lot of large projects like the Linux project were using to manage their source control. And in 2005, in April, BitKeeper changed their licensing model to make it so that the Linux project could no longer use the software for free. And so immediately Linus, who you know from Linux, he began developing Git in, let's say, April of 2005. And at the same time, another team began developing Mercurial. Both of those were aimed at being the de facto source control for the Linux project. And in the end, Git was the one that was selected, and Mercurial, while it's still around, it's used by a very, very small percentage of projects these days. Git is now the most popular software repository management tool, and it's probably used on 95 to 98% of all the projects out there. Okay, so that was just the little history lesson I wanted to do before we got started. Git has some great features built into it. So all of the things that you are familiar with, like creating a repository by doing git init, being able to commit changes into that repository, being able to push those changes to another directory on your server, having two people being able to have copies of the repo on the same server, and being able to pull copies from each other and merge changes between them. So there's a lot of great stuff that Git does out of the box. And if you want to move to like sort of a server model, you can basically just set up a web server to host Git. In the very basic version, clicking on the wrong thing here. In the very basic version of a hosted Git service that we might build, we're going to have some kind of server somewhere that's going to probably be a Linux machine that will run the Git commands like git clone and git merge and git commit when it receives input from the user community. But that's obviously going to have some kind of web front end that is going to allow people to connect with a web browser. And so we'll need to have some kind of web server that responds to HTTP and HTTPS requests. And if someone, let's say, goes to a URL, let's get a little cloud here. So let's say someone goes to a URL like github.com, org name, repo name, and they try to do like a git pull. So that's going to have to go to some web server that is listening on github.com, and it's going to have to serve up the content that is in this repository called repo name that's owned by this organization. So this web server is going to have some kind of logic in it that's going to be able to tell which user this is. And then it's going to have some kind of logic to determine where exactly is this repo stored in the backend somewhere. And then it's going to have to use Git to go to that location where the data is stored in order to start interacting with that repo on behalf of the user. So we're going to have some kind of storage system on the back end that's going to store all these things at the very least. And so when users talk to the web server is going to have an application on it that knows how to convert that to talk to the Git service. And then the Git service is going to have to be able to go find the location somewhere where the files are stored in order to serve up the commands. So in this model, if someone did, as we were saying here, if this was like a git clone of this repo, then it's going to be basically an HTTP GET request for this, and the content that should be served back is the directory listing of the repo. So, so we have a few components here. Do you have a question?
Yeah, just a quick question. So essentially, like storage in this case would be GCS, right, or something like this, or?
That is a great question. So, if I'm thinking about this, like if I'm trying to invent GitHub from scratch, I know I have the git command, and so I'm gonna running that somewhere. So this is probably running on some kind of let's say like a Linux server, most likely. And then normally when I run git on my machine, I just cd to some directory path and I do like the git commands there. So so it might make sense to store it on a file system if I have to like be able to cd into the directory, or if we want to store it in a bucket, we could do that, and then we could access the storage using something like GCS views. So if this was like, let's say a Google bucket, for example, where the data is stored, that's like a bunch of objects just sitting in a file structure somewhere. And so I can request individual objects if I want. But when I need to work with the repo, I clearly need the whole repo all at once. So there's a few things you could do. I mean, you could imagine maybe like zipping the repo and just putting the repo as a zip file in the bucket. And when this user makes the command, what this Git service would have to do is it would like pull down the zip file from the bucket and expand it. And then suddenly like it would have the repo, you know, stored right in the correct location on disk. Then it can do a push or edit a file and commit it or whatever's necessary. It could just pull it, serve it through the web server. So that's a very simple approach that would certainly support like a Git pull, for example, or a Git clone.
Yeah, so essentially GCS views, it's like mounting files.
Yeah, so instead of using a zip file, we could use GCS views, and we could actually just have the entire repo not in a zip, but expanded as all the different little files that are located in there. And we could just mount it somewhere. So like on this Linux server, we could mount that in like /mount /org name /repo name, for example. And so now we've mounted that file system. We go into that directory and we can serve up those files.
Yeah.
So that's a pretty obvious way that you might do that. And that does make a lot of sense because of the fact that, you know, Git is file based and these are files sitting in a bucket. So I like that as an initial approach.
Yeah, that makes sense. Also, there was a quick question about the history part. So do like big organizations like Facebook and Google have their own modified Git system, or no?
Yes, in general, those big companies do. Like Google is slightly unique in their approach because Google uses something called a mono repo. So whereas in your use of GitHub, you might, each new project you create, you might have a new repo for it, and that's where you keep the issues, and that's where you have the code for that particular system, and then you have a second repo where you have a different bunch of code in there. Well, in Google, they use a mono repo, so the entire code base is in one repository. So obviously it's extremely large. That code base has like the code for Gmail in it, and it has the code for, you know, Google Cloud Run, and all the different services are like in that one code base. So when they commit a change, like in maybe a typical or a more typical use case, where you have like a single repo for each project, I commit a change with this project, and you know, some kind of Git action or cloud build job runs, and it does the tests and it runs the build and it pushes out the code for my app. But in Google, like every commit is all committing to the same repo. And so it has to have an extremely complicated set of policies about like which commits cause which apps to deploy and which conditions, and then how that code base directly interfaces with their sort of deployment flow of like approval process for when an app is ready to get approved. And when they do the rollout, they have a very complicated process of how like the product is rolled out to a small percentage of users and then a growingly larger over a period of time, so that they can find errors and stuff. So those code bases are highly modified from just using the basic Git open source. I think maybe I'm not sure about this, but it might be that Google's tool might be based on Mercurial as the core unit, potentially. I'm not certain, but in addition to their monolith code base that they have, like Google has many open source tools and libraries and other things, and those all do use Git, because those are all hosted on GitHub, just like many other projects. But yeah, those massive, you know, FANG companies, they're starting out with these same tools that we're familiar with, but then they like modify them so heavily. Like, you know, like Facebook uses PHP, but they don't just run the same PHP that you and I run. Like they have a heavily kernel modified version of it that runs in a, you know, at scale. And so, yeah, you will find very heavily modified versions of some of these tools in use at the big companies for sure.
Yeah, makes sense. Cool.
Okay, so in this model, I think we have an idea where like a user who's sitting in a computer or even a web browser could go to some kind of web server. That server would know how to send it to some kind of interface with Git, like a thing that knows who users are and where their things are stored. And then that thing would eventually be able to talk to the backend bucket or something where the files are stored, either over GCS views or some mechanism. And then it could serve those files to the user. And so that's great. I think like it may get a little more interesting when we start thinking about pushing something. Because that is going to involve like actually making changes to the files. And so we'll have to consider if this still supports that. But there is another thing we need to add here, which is SSH. So when you use Git, there's a few protocols that Git uses when it connects to a server. The most basic protocol is local, where it just goes to another path on the same machine that you're on right now. So there might be a directory that our team uses where we keep the like primary source code that everyone shares, and then we each have our copies of it, and then we might just push it to that other directory when we're going live. That's a local installation. Git has a very basic, like, I think it's called dumb HTTP in their docs protocol, which is just for reading. So that just does what we have here. It lets you pull the repo down. And that's the protocol that makes it so that you can just do a git pull on any public repo
Mhm.
with just an HTTP command, and it'll just pull down the code. If you try to push in the same way, then it's going to engage some kind of authentication process. And so when you're using HTTP, if your Git URL, like we have in this example, is using like an HTTPS string when you do git clone, then a private repo that is hosted there would request authentication, but it would be maybe something like user password authentication, or maybe like an API token, or maybe some kind of OAuth and authentication, where maybe the app pops up a thing that says this app is requesting access to something, and the user has to like approve a scope or something like that. So there's a few ways that an HTTPS user might authenticate, but then these same users, like, they might also come here over HTTPS. And so that would be like, for example, if they did git clone git at github.com/org name repo.
Mhm.
That version of the URL there, that's going to use a SSH connection.
Mhm.
And so it's not coming in over HTTPS, it's coming over SSH, which is TCP port 22. And this obviously is TCP port 80 and 443. And so this is a whole different interface. This is going to do authentication, via SSH keys. And so there's going to be a whole mechanism that we're going to have to build so that a user can go into their account and click on the settings and then add in an SSH public key into their account,
Mhm.
that then they would use that SSH private key to authenticate. And so this system would have to have understanding of the SSH protocol and the private keys in order to log the user in. So for example, if we're building this from scratch, we're going to have a Linux machine that has OpenSSH running on it.
Mhm.
Um, OpenSSH uses the password database on the Linux machine to know who the users are and what their home directories are. So what we would do in this model is we would have, maybe this is the same like Git service. These two services here, they might be the same like thing. But this one is going to have to know about like home directories, like home org name or something. It's going to have to know about the .ssh directory and the authorized keys file.
Mhm.
Um, and it's going to have the user, like, let's say the user is org name. In the password file on that machine, so that when they log in, the OpenSSH command can check the .ssh authorized keys directory in that path and determine if the user is authorized or not. So that maybe that is an offshoot of this this Git auth service, where it actually handles the Linux authentication and lets the user open the SSH connection to the server.
Mhm.
Um,
Just a quick question. So you're saying we need to have, ideally, we need to have two servers, like one that serves HTTP requests and the other one is SSH, or as you said, we can merge them, or like when do we split them if we need to, like
well, so part of the reason is that most likely between our users and our oh, this was the git clone https github.com org name repo. Between our users and these primary services, port 80 and 443 and port 22, there's going to be some kind of load balancer service. So because these will probably be a farm of servers. Like, I don't think that every single, like, if you have 45 million repositories, then you're probably not going to have 45 million users on a single machine. Like, in this case, what we're talking about with these like home directories model, where we have password users that are in the password file on the computer, and they have a home directory. Like, Linux has a limitation of like 65,000 users in the password file.
Yeah.
Because of like the number of bits that are allocated in the operating system to store users. So there's no way we could have all 45 million repos on the same machine, because we can't have that many users necessarily on a single computer. So there's going to have to be some kind of like load balancing situation here, and effectively like load balancing a SSH connection and load balancing an HTTPS connection, those are not really the same thing. Like, if you're using a Google load balancer technology, for example, one of those would use the HTTP load balancer, which is like a normal thing. The other one would have to use the TCP load balancer, and that's sort of like a different technology. So the endpoints that serve port 443 and port 22, those will probably be different farms of systems.
I see.
And so we might have load balancing here, and then we might have like load balancing here as well.
So essentially, if we are talking about the system that has only like 10 users or something, it's okay to have those two servers merged.
Yeah, and what I would say is, like, the way you should think about this is not exactly how do I get rid of this little e that keeps dangling here? There we go. These could be microservices. So, like, if we think about this system here getting deployed, let's say, in a Kubernetes cluster, which is one way you could deploy it. These could be different services running inside the Kubernetes cluster. And then each one could have their own set of instances potentially behind it. If you're running all on one machine, then these are just different processes that are running on that same computer. So you'll have one HTTP process. Let's say this might be Apache or Nginx or something like that. This would be running something like OpenSSH. So those are just distinctly different services. If we were building GitHub for millions of users, then those services would be in their own cluster, and they would have their own, load balancing and scaling. They would be sized appropriately for whatever they need to do. So, for example, like, if we have 65 million users, or I think that's how many repos they have, so it's probably fewer users, but you might have to shard the SSH services out. So there's a Linux machine. Hold on, someone's at my door. I'm sorry. Hi.
Yeah, in the meantime, if any one of you has any questions, feel free to drop in the chat, and then, yeah.
I apologize.
Oh, good.
The mailman just showed up. Okay, so if you did have a large number of users like GitHub has, then you might have each server might have like 50,000 home directories on it to handle SSH, and so you might just have a farm of them, and that means the load balancer for SSH, it would have to have a way of like getting injected into the SSH protocol before it hits the server, and knowing like who's trying to authenticate, and then directing the traffic to the server where that person's home directory is stored, for example.
So I'm sure if you're going to cover that, but a quick question about like redundancy. Is there any redundancy in terms of like duplication of users' data on multiple machines, or it's only like one machine that has their like directory with all the files, let's say?
That's a good question. So there's a few places that we could handle that. Obviously, we don't want to ever risk a situation where we might lose a customer's data. Like essentially, if we just break it down to what is the purpose of using a Git service at all, like the most basic reason you might use one is it's like a safe place to store your repo, so that
Yeah.
it's not only on your computer. That's like the core feature. So without any other things, like I just need to know that it's going to be there next time when I do a poll. So you're correct that that's of the utmost importance. Now, when we select our Google bucket, we have some options there. I can select a bucket, for example, that is in the US multi-region. And so that by nature, the data in that, when I write a file in that bucket, Google is storing it in 3 physical locations around the country. So that if the data center in Ohio completely gets blown off the face of the earth, Google has a copy of it in 2 other regions. So that way the file will not be lost. I pay a premium for that capability. But that's the most basic way you could do it, is just rely on the redundancy that is built into the underlying storage that you're using. But there's other things that could happen. For example, like we could write some bad code in this Git service that we have to build, and it could delete the wrong repo when it meant to delete a different repo. And so now it doesn't matter that Google has redundant copies, because Google didn't lose the file. We deleted the file, and then Google did what we wanted, and they went ahead and deleted it. So there's a few things you could do with your bucket. Even if you're just using this US multi-region bucket, you can add versioning on the bucket. So that way it keeps versions of files. So if someone deletes a file, you still have the old version. If someone uploads an incorrect version of the file, you still can go back. So that gives you some protection. Also, Google recently released a feature in cloud storage that is like a delayed delete. It's like a trash folder kind of situation. And so by default today, if you create a new bucket, then that bucket has this 7-day delete protection on it. So when you delete the bucket, you continue to pay for the storage for 7 days, but it's also recoverable during all those 7 days. So that's one way you could protect it. And then of course, like we could be even more thorough, and we could have 2 different buckets where we store the data. Or in fact, we could have a second cloud. So like when I began working with Google, I joined a lot of these customer advisory boards, because I was working at a company that was a very large customer of Google Cloud. And so we would get invited to these advisory boards. And I remember one of those advisory boards, there was someone from Netflix there. And you guys did a Netflix discussion recently. But I was a little bit baffled, because Netflix is like well known as one of the very largest AWS customers. And so I'm like, what are they even doing here? But Netflix, like as much as they loved AWS, like out of just pure caution, they kept their tertiary backup in Google. So they would have like the primary version of all the movies, stored in like a bucket in Amazon. And then they would have a backup bucket in Amazon in a different region, so that if they had an outage in the primary region, then they would still have another copy in Amazon. But then, like, if perchance like Amazon disappeared from the face of the earth, then they still had a copy in a different cloud provider. And so that's certainly like an approach you could take in this situation. The other thing to consider, and I know this was covered a lot in the Netflix discussion, is are the users only going to be in the United States? Or are we going to have people that are accessing the system from other countries? If we are, then we have to consider, like, if we want to introduce a CDN, as you talked about earlier, or at least maybe we want to have copies of the data in the US and in the EU region, or maybe in Asia. And that could obviously vastly increase your cost if you're storing everything like in all these different locations. So then it could just be a question of like, how quickly do you need to be able to serve up a piece of content? And if you do need to be able to serve up a piece of content quickly, then are there ways you can do that without always having it close? And CDN or some form of caching is certainly a way to do that.
Yeah. One last question before we continue is, so this second Git service, right, that you have for SSH, is it connected to GCS as well, or no?
Yeah, I mean, I think ultimately what's going to happen is that the reason I put these both in pink is there's some kind of brain that you're going to need. Like, these services out here, they know how to handle HTTP requests. They know how to serve up web pages, things like that. But there's some unit in the middle, which is like the core piece of software that you need to write to build this thing. Because Git is free. Git exists. Like, we have that. But the thing that needs to live in the middle, which is probably this one service most likely, is something that understands who a user is. Where in the world is that user's data stored? What are the sort of access permissions associated with that user? And with a repo, like if a repo, let's say a repo is not public, let's say a repo is private, and it has like 10 Git users who are collaborators, and it has 2 teams that are collaborators. Like, something in this architecture needs to be the single place of truth that knows how to determine who's allowed to access this repo. So that thing is going to have like a database behind it of some kind. That database is going to have like a list of who all the users are, what repos they have that are assigned to them, all the permissions that are associated with all the repos and the users and the teams and the orgs. That's all going to have to be in some kind of database with an app in front of it that's the gatekeeper of everything related to a repo. So like, if someone comes in through SSH and they're going to do something and they auth, and that's great. After you've gotten that far, then you need to like be like, where is their repo so I can start doing something with it? And that's probably what this interim service does. So like, we could probably just delete this and say like, that's the brain, and the OpenSSH service has to talk to that thing, and that thing is what knows how to talk to the storage, and that thing is also what knows how to talk to the database. And so, whoops, I'm not apparently an expert at Lucidchart, but this is like going to be the gatekeeper of all of the access to actual data from any of these different interfaces.
But I remember you mentioned that the reason why we put like another server right in pink was because it would run like different systems, so it wouldn't be a Linux server, right? If I recall correctly.
No, so far I think we have a lot of Linux servers. We have,
so it would be able to serve SSH as well.
Yeah,
right?
yeah, for sure. So like, if I just have it, like, would it make sense if we focused on designing this as a single server model instead of as a like scalable cloud model where it would just run on one VM?
Yeah, I think we can do like the basic overview here, and then we can briefly like mention how we can scale it, like at least give with a few comments. But yeah.
Okay, so then I would change this a little bit. Let's just start with a Linux server here. Okay, and that server would run a bunch of services. It would run Apache to serve HTTP and HTTPS. It would run OpenSSH to serve the SSH connections. It would have some kind of database, let's say maybe MySQL database running on it. It would have a large disk, like a big home disk with enough space for all of the storage, anyone's repositories and all the commits and everything like that. So, you know, a large like disk, however big you would need. And all of that would run on a single Linux server. So it would really, like, the server would just be one box and it would have a few different services on it. And so all these boxes are just, if we were scaling it out to be like some kind of cloud thing. So we can focus on this model here. So basically we have a Linux server, it has Apache on it, it has the Git command installed on it. If someone hits the web server, we can write a web app that translates the URL request and then subs out to the Unix system and just runs the correct Git command, like git clone or git pull or git merge or whatever it may be. And so those would all just be different processes running on the same server. So this is port 80 and 443. This is running on port 22. We have the SQL Server running on 3306. And then the disk, that's probably just like a big, you know, dev SDA disk that's mounted in /home. And then inside the disk, you would have a home directory for each user. So like home username. And then inside the home directory for each user, you would have home username, repo, one, and so forth. So it would just be like a home directory with a subdirectory for each one of the users. And that you would just store on the local disk on the machine. We would do snapshots on a regular basis. We could, in Google Cloud, you can take the disk that you're using to run and just have it run snapshots every hour or whatever, so that if there's any kind of issue with the disk that you're using, you can always go back to the most recent copy of the data. So that's how you'll get your data protection. Okay, so now on this server, if someone wants to do a pull request, that's not actually a feature so much of Git. I mean, it is. So like in the Git command, the open source tool that we're using to build all this on, there is something. It's called git request pull. And so you would run git request pull and you would tell it the commit to start from, like where the remote repo that you're trying to have pull your code into it. It would tell them which commit ID they have on their end that you have on your end that your commit is starting from. It would be the URL that you have your commit hosted on, and then it would be the commit that is the end of when you want the request to pull. If you don't provide the last commit, then it would be like all the commits that follow this commit. So you would run this command in Git, and then Git would return back text. So it will give you text that you can then email to the person that says, hey, Alexander, can you please pull this repo from the place where I have it hosted? And so that's not, I don't think we can really use that. We have to build our own pull request feature to do something like what GitHub does. So let's think about how that will work. So in order to do a pull request, you have a source repo where the new code is, and you have a destination repo / branch where the code wants to go. And so you're going to be able, you're going to want to take code that is in the source branch and get it into the destination branch by asking the destination branch to pull the code into their branch. That's effectively what that process involves. And
But you said
so
we cannot use the git command, right? If we are building like a clone of GitHub, so you're saying it's not doing that behind the scenes, or it is?
well, this is how the process works. Like someone has a repository with code in it. There's another repository, or it could be the same repository in a different branch that has code in it. And the person who made the new code wants their code to be in the other place. Like, let's say my code is in my feature branch and I want to get it into the main branch. So the way I initiate that process as the person who developed the new change is I ask the people who own the main repo to please pull my code in. That's just the definition of what a pull request is. It's not like the technical implementation. So what happens in GitHub, like I guess we could just look at a pull request in GitHub. Let's see if I have one recently that I did. Here's a pull request. And so there were some changes. So we basically need to build this feature into our app. And so what that means is you need a way first to say like, which thing are you asking to merge into which thing? And so like when you are creating a pull request, let's see, new pull request, then you're basically taking code from some branch that you have and you're merging it into some other branch that you have. That's like the initiation process. That's the same, sort of effectively the same thing as running that little git pull request command. It's like I need to be able to tell someone that I want to do this merge. And so then all that does is like create this object in the system, which is effectively like a list of all the changes that occurred from your commit to the other commit. So the way I would implement that on my machine is, you know, I would literally do like I was describing this git command does. I would go to the place where now I'm the person polling. Now I'm the person who owns like the main, like the way we should think about this typically is like there's some open source project that is out in the wild and there's a person who has contributed to it. And the way they did that is first they had to clone the repo. And they have their own copy of the repo that they're working with. They make a bunch of changes. Now they've done a commit, which only exists in their local copy. And it represents all the changes they did. And they want everything associated with that commit to make it into the upstream place where the people who are maintaining the open source project live. So now if I'm the maintainer of the open source project and I'm going to do the pull request, like the way I do that is I first set my git remote to the place where you have your code stored in your repo, which let's say that's in your GitHub account or something. I pull those changes down to my local machine where I have the repo with all of the previous changes. And then I literally just run a git merge in my local directory of the changes from branch A into branch B. And then Git, as part of the open source tool, will do the thing of being like, OMG, there's issues with this thing because something changed and they're conflicting things. Like that's all that of like understanding what can and cannot be merged and what is the problem with the merge, like where the merge conflicts exist. That's all built into Git. So we don't have to build any of that. We just have to build the thing where we like
essentially a wrapper, right?
Yeah, a wrapper that so the wrapper would like clone the repo, the main repo down to a place. It would pull down the the source repo that has the other stuff in it, and then it would do a merge between those two, and it's effectively pulling two branches in the same repo. And it would do a merge between those two, and like then it would react to the output of that command. So if it attempts to merge and get like the Git response says, no, there's some conflicts, here's some conflicts, then it would like understand the text of that response, and it would display that in a useful, smart way to the web user who's sitting in the console. So if there was that merge conflict, it's taking just the raw output from Git merge, and then it's translating it into this beautiful interface here.
Yeah, makes sense.
And there's a lot going on here besides just like comparing two branches and showing you the changes. There's also the ability to comment on any of the changes. So I can come in here and be like, oh no, there's a bug, in version 0.6.6, so we need to roll this back. And then like me and the team can have a whole conversation about this line of text in the commit. And so this is when you start to realize that like you might not just be able to have everything like as only a text file in the system, like you might need everything to be in a database, because when I hit, add this single comment here, there's some database, some table in our database that is going to get a new row in it. And that row is like a comment on this org, on this repo, on this branch, on this file, on this line. So you need a database structure that can hone in on a single line and a single commit and a single change, and they can add all the comment structure to that. And so clearly you're not going to be storing that like in the Git folder with the repo in the text files there. That's going to have to go in some kind of database.
Storage, but with the reference essentially.
Yeah, exactly. So let's get back to the chart here. So in the basic sense, you're just going to have, let's say maybe a bash or Python wrapper around the Git commands or the Git libraries, and you're just going to parse the output of those commands and then give the user as much like rich insights into what's going on there as you can, like give them the ability to comment, give them the ability, like another hard part about this is dealing with the merge conflicts. So just literally like not even thinking about the technology behind it. Like if you're a developer and you're in a situation where you have merge conflicts, that is stressful and difficult to deal with. And sometimes it's a lot of work of like going in and accepting each and every change that came through since, the conflict happened. And so I think like creating an experience where not only the user can see all the details of the pull request and the potential merge and the errors that happen. But Git can often or GitHub can often resolve those changes. Like it will walk through all that manual step, and because it'll say like, oh no, there are merge conflicts. Would you like me to manually resolve? And then if you click yes and it successfully does it, one, like it just saved your life of potentially a whole lot of pain and suffering. But two, like that's kind of a challenging thing because it's going to then have to walk through the commit history, go through all the changes, and then validate, like based on when your change came in and when the other person's change came in, which one it thinks is most likely the correct one. And so it's adding a lot of smarts on top of what the Git open source tool is doing. Because if you were trying to resolve that issue in your local Git, then it would really be a very manual process. But GitHub kind of almost makes that invisible. So that's a whole tool that we would build in the pull request thing that would understand all the context of those changes, and so forth. Like, in Git, you can just run git diff, and you have your working directory, and then you have the committed version, and it'll tell you everything that's different about it. So that's great. You can just parse that and show that to the user. But yeah, then being able to resolve potential commits in there automatically is magic, kind of.
So it's a separate service essentially, right?
It's another piece of software that would have that intellect to be able to churn on that. So imagine like the default model is what we talked about. It would just like pull the two branches into one directory. It would attempt to merge. And if it successfully merged, then it would give you a green thumbs up. And if it failed, then it would just be like, I'm sorry, the merge failed. It's your problem. And then the way you would do that is you would like go into your source code directory and you would make a bunch of new commits that fix the rollback, the changes or whatever. And then you would try to push it again. And then you would try to do the pull request again. And if it merges, great, but if it doesn't, then that's where you'd have some kind of smart piece of software that GitHub had to build that would say, okay, let me take this situation where there's a merge conflict, and then let me run this other, piece of software against that conflict and see if I can automatically resolve it. So, if there's a thing most people do when they have merge conflicts, that's the manual process. That tool is going to try to run through the same exact flow that a normal person might do in an automated fashion. And then you would just keep evolving that. Like you would see like of the merge conflicts that do happen, how many of them is our magic tool able to resolve on its own? And then you would keep making the tool better and find more of those edge cases so it can resolve as many as possible.
Also, since we have two other topics left for search and CI/CD, maybe let's summarize like everything that we talked about right now. So let's like, for example, right, we talked about clones, we talked about pull requests, we talked about branches, we talked about like commits, right? So for example, so for cloning, you said that, okay, so we have one load balancer for HTTPS requests, then, or I guess load balancer for HTTPS requests, then load balancer for SSH requests. Then we have a server that essentially is like the brain of the system, and it knows, okay, give this person access to that branch or repo or anything like this, right? Which is in pink here. And then you also so database stores like all the data about access and like comments, as you said. But Google Bucket, so GCS would be the one who can store like the actual repos with GCS views, right? And the way we would structure like different branches, if I understood correctly, would be like, or different repos, right? It would be org name, as you mentioned here, right? Then repo, branch, and then I guess, can it be down to commit then? So since like technically each commit is a replica of the system?
Well, no. The Git, like when you have a source code repository with your some code in it, and there's inside that code base, there's a .git folder in there. In there is every commit that's ever happened that you've ever pulled down. So really, like, to store the thing, we just need to store a copy of the most recent most recent directory. If someone does a push, then we're going to get our copy that we have stored and we're going to push into it and then save it. And so now that's the most recent version on GitHub. Obviously, like, other people in their local, they have more recent code that they haven't pushed yet. But as far as what has been pushed to GitHub, it would just be one directory for every repository.
So essentially we delegate all of this like managing of commits and branches to Git itself, right?
Correct. Like, in the end of the day, we really just have to tend to this directory, which is the most recent copy of the repo, and make sure that we know how to find it and that it is the most recent copy. Whenever we're going to do an action like pull, we just have to go find that directory and read from it. Whenever we're going to do some other action like a commit or a push or a merge or a PR, like, we're going to have our copy. We're going to have to probably bring in, like, pull down some changes into our copy, which now are in there, and then do the merge right there, or do the make a new branch. Like, if someone goes into the GitHub web interface and they say, I want to create a new branch, then it's going to go to the directory where the repo is, and it's going to do git branch, like git checkout -b new branch name. And then it'll make sure that's stored somewhere. I think, we kind of did talk about two different models here. So on the left-hand side, we're talking about like a cloud system where potentially each component could be its own machine or its own cluster of machines. And these are sort of the components of that system. That's why having like the bucket in the US region, that's kind of compelling. In fact, like, if we were doing this at scale, we might have one bucket for each user, or maybe even one bucket for each repo. Those are both possible options. But if we're doing it on a single machine, we might just have one /home disk with a home directory for each user and a subdirectory for each repo. That would be a fine way to organize it if you weren't doing it at massive scale. Perfectly acceptable.
And maybe one last question before we move on. So you put like pull requests outside, so on the right side, right, on the small diagram.
It's kind of like a sort of a function diagram. It's not really a component.
Okay, so but what in this per pink box, what the part of what it would be then?
So basically, like, I think what would have to happen is that thing that that wrapper that goes around a pull request and knows how to read the output of an attempted merge and potentially handle that would all be part of this, like, the brains here. The Git, like, brains. So I think that's just like a piece of functionality that service provides.
But I guess as we scale, like, technically we can have like services, right, or microservices that would be like responsible for pull requests, for, I don't know, for other things that we discussed. So
yeah, like, one thing to look at, actually, if people want to do additional research on their own about like how some of this works, GitLab, which is not GitHub, it's another competitor, but they did what we're doing today, right? The people at GitLab, they got into a room and they were like, how would you build GitHub? And then they did it. And now it's like a competitive product. So, like, this is maybe the second or third most popular Git service out there. So they have gone into some effort to describe their stack, like how it works. And it's kind of an interesting read. They even have a diagram on here, which doesn't look that dissimilar to what we've been building. But these are the actual components of the GitLab service. And like, they have the thing that I was calling the brain that's the GitLab workhorse. Like that's what they call it. And they have something, their data is stored in a Postgres database, and they have a Redis database for caching. And they have this thing that is the magic that knows where every repo is and who has access to it and which bucket it's in and all that, called Gitly. And so you can go into some detail and actually read like about the different services. It's nice that GitLab has offered that. That did help me a little bit in preparing for this, as I'm sure you can see here. Another thing that we haven't talked about, which is potentially relevant, is like GitHub and GitLab have a thing called Pages, where you can have like a static website that you host easily on their platform. And so that is just like potentially like another web server that's sitting somewhere. And when you're doing a commit, if you do like an action where you're committing a change to one of these repos that has Pages enabled on it, which you would know from the database, then you take the content from that directory, and instead of just storing it in the Git repo, you also go put it on a web server somewhere, a public web server. And so that's how all those web pages are stored. When someone makes a change to the code and they have a Pages directory in there that's configured, then not only does the repo get updated, but also the website gets updated. So there's some doc root on some server with a Apache running in front of it that serves all that up. Okay, cool.
Yeah, that's a good diagram. If you can share it with me afterwards, I'll share it with the chat as well.
Yeah, I have a few links that are I think people will find interesting that I will share with you.
Cool, thank you.
Okay, so let's see. So I guess we'll look at search next. This is kind of a tough one because the search is really quite magic in GitHub. Like this is some search I did. I was looking at a page here. I found some commit I was working on, and then I have this get collection. It's calling some function called get collection here. And like this is also showing me like a different file in the repo where there is that function defined, the function I was calling in that part of the repo. So like this has an intense amount of understanding about not just like, it's not just storing a Git folder somewhere with a repo in it. It's indexing like every single aspect about the code. Not only does it know every line that has the string get collection dict in it, so I can search and find every single file that has that string in it, but it knows which one is defining the Python function. So like I just the reason I wanted to put search on here is because it's kind of a difficult problem. And like I wanted to think through like how would you index that? Like
this is basically the core problem, right? Like indexing and then
indexing, exactly. So like if we understand that we're gonna have this database, I should probably make it bigger because it's probably like a big deal. Maybe it's not as big as the bucket though, but we're gonna have this database that's gonna have, you know, potentially millions of rows in it, because not only are we gonna have a list of every user and a list of every repo and a list of every team and, you know, the list of people who have access on a given repo and in a given org, like all that's stored in the database. But most likely we're also logging every single commit that happens and putting all that into the database. We're also probably logging all the comments that everyone has made. And then when someone is typing in a search term, it's searching the files, it's searching the issues that are in the database, it's searching the comments that people made, and like in binary files that you have too. Like there's a lot of stuff in that search index. And so there's no way you could just do like a select all from database because your query would have to basically select from every table, from every field, if any field it matches the string. So that's just not a SQL database problem. Like that's a search problem. And so generally what you have to do is you introduce like another component into the system. Now this doesn't have to be like we talked about, this whole thing could run on a single server with just a bunch of different services running. It could run in a Kubernetes cluster on a single server, or on a small cluster, or on a large cluster. Like there's a lot of ways to do it, but there is another piece of software that needs to exist in order to do the search. So we're gonna put that over here, and we're gonna say that like the brains kind of needs to talk to that, probably in both directions, I would say. Like the brains needs to talk to the search, and the search needs to talk to brains, and they're probably tightly integrated. If you're just choosing a tool for this, most likely most places I think would use something like Elasticsearch. So if folks aren't familiar with that, it's a piece of software. It's basically good at taking all your data that you have, whether it's structured data in a database or just like freeform data, text, things like that, and files and other things. It's really good at making a searchable index of all the data that's fast. That's kind of what Elastic does. In fact, if people aren't all that familiar with it, I'll just load up their webpage so you can see they're fairly de facto solution in this space. They have an open source product, and they have a commercial product as well. But basically what that's going to do is you're going to spend some time having Elastic like index everything that you have. So it's going to make these kind of text blobs of all the data, and it's going to make it searchable using free text kind of search. So it doesn't have to be like SQL query, but it could just be like anything that mentions this date or anything that mentions this word, no matter if it's a file or an issue or whatever. And it'll make a massive index of the searchable stuff, and it'll be fast, and it'll be separate from the database. So it'll also have like its own big, data store of some kind behind it that it uses to store all the indexes.
So it wouldn't be connected to our actual database. It's rather it would have its own.
Yeah, it would have its own database. Probably more like a probably like not like a SQL database, more like a document database, like a key value store type thing, where you like assemble all the relevant data about an object into one document. And then if that document matches, then you know that like that object matches. So yeah, but you're effectively going to have to, make a copy of the database, like at least the parts that need to be referenced in search. And then Elastic is gonna, have a different index of the thing. The way you think about it is like you would, when the user types in a search term, you would probably take that search term and send it over to Elastic, and Elastic is going to give you some, like, let's say IDs or URLs of documents or objects in the world that match, and then you'll go to the database to go get those objects. Like Elastic won't have the entire complete representation of all the objects. It'll just have like the necessary information to index them. If that makes sense. But basically, like, yes.
Essentially, we delegate this entire process of search to this service, right?
Yeah, to this service. And then so there's the initial, like, deploying search initially is this complicated process of like, what are all the things that we want to be searchable? Let's pull those things into Elastic. and then let's build indexes that like appropriately organize the data. So when people do the searches that we expect that they will want to do, they get back these reasonable results. And so there's like a whole process of tuning that and getting it to behave how you want. And then you go live with it and you're like, great, we have search. And it searches everything because we spent months cataloging all the data into Elastic. And then as soon as you deploy it, someone commits a change to something. And so now the question is like, how does that get into the search index, the change that just came in? So then you can imagine that like in this brains, like every time someone makes a change that would in some way impact like a search result, then there's going to have to be some kind of trigger from the brains that's telling search, hey, Lucas just committed this new file and it has yet another instance of get collection dict in it. So tomorrow when someone searches for get collection dict, we want this new file to be included in the results. And so there's going to have to be a way for the brains to know that something relevant just came through as a change. And then it's going to have to tell the search index to go like index that new file.
Okay, so essentially like this brain is still responsible for pinging this search.
Yeah, like I think the thing that I'm calling the brain is like nothing can touch a repo without that brain being the decider on
approval. Yeah.
And so that means that that central piece of software will be aware of all the changes because it gatekeeps them. So because it knows that like Lucas just committed something to this repo, it also knows like who has access to that repo. So it can take the relevant information that it knows because it's the brain, and then it can tell Elastic like there's this repo that 6 people have access to. There's this one file that just got changed. I need you to update the index so that when those 6 people, do a search, this file is included in the results. And so that the advantage of having that central component that is the hub that all the other microservices have to talk to, that gatekeeps access to Git, is that it's in a position to know everything. So it can like notify that other service that something happened, or it can notify, like we'll get into this in a moment when we talk about the CI/CD, but there's a lot of things that will occur in GitHub, like an event that generates some kind of other event. So like, there's the Dependabot tool, which we won't dig into, but it goes through and it sees like, oh, you're using a library that has a bug in it. And so then a notification comes up. And when I do a commit, like there might be someone who's watching the repo, and then they get a notification in their Git that says Lucas did a commit. And then which we'll talk about as we move into the CI/CD, like I'm going to do a commit and that's going to kick off like a GitHub action, which is going to run something. And so there's this need to be able to do kind of alerting or notifying or triggering on these different repository events. And that's, again, why you need everything to go through some kind of central thing, because there's all those interdependencies. Like if I'm about to merge from the dev branch to the prod branch right now, and you commit a change right now to the dev branch, then what is supposed to happen is that if I click merge after you, your new change that was added is part of this PR that I'm now making. That's how it works. And in order to ensure that like I don't merge a change when there's already been a commit that wrote over something, that has to be gate kept, so that, because again, at scale, you could imagine that I'm accessing the repo and you're accessing the repo, but we're not both hitting the exact same web server. Like you might be in Canada and you might be hitting a web server that's in the North America region, and I might be hitting a web server in the East region. And if those two web servers have a different idea of what the current state of the repo is, then we would get into a disaster. So both of those web servers have to talk to home base and to say like, hey, does anyone make changes to this repo recently? And so again, that's why you need all this central control, the hub in the middle.
Yeah.
Okay, so we're pretty tight on time, so let's start talking about CI/CD here.
Yeah, just like a brief high-level overview.
Yeah.
Of just what the key problem is and what.
Yeah, so I'm not going to build this out necessarily as part of the diagram, but as we talked about, like there's going to be some kind of event that will trigger something like, you know, a commit or a merge or something, and it will kick off a GitHub action. That's effectively what actions is and what the CI/CD process is. And the most typical way to think about that is like I have a dev version of my application and a production version. And when I have just tested some changes in my local, I push them to dev, and I'm allowed to do that, and that's great. And when I push it to dev, there's a action that kicks off which builds my software that I wrote, and it pushes it into the dev like web server, let's say. And then I can like Slack the team and be like, hey, I pushed the changes to dev, you know, let's all test them and see how the changes look. And then later, after we're good with those changes, someone's going to make a PR where they say they want to pull all the changes from dev into prod. And then when that PR gets merged, it's going to then do another GitHub action, which is going to do the build and the push, but it's going to push it to the production web server. And so those are two different GitHub actions in this model that would run under different circumstances. In this case, that depends on which branch committing to. There's any number of conditions that it could depend on. So it could depend on the name of the branch. Like if your branch starts with the word test, then you do this thing. And if your branch starts with something else, then you do this other thing. It could be a tag that's on the commit. Like there's a lot of different ways you could trigger an action. But let's say like on push, you know, we're going to trigger an action. So this brains thing over here, it would say, okay, someone just pushed, like Lucas just pushed a commit to this particular repo. And then it would have to know, okay, well, that repo has a GitHub action set up, and it has a condition which matches the current condition. So the brains would say, okay, we have to do something about this. And then ostensibly it would, let's just move this out of the way a little bit. It would probably send something over to the CI/CD service. And so let's say there's actually an event. Whoops, really not very good at Lucid. So GitBrains, you know, says, oh, we had an event, and the event triggers some kind of CI/CD thing. So this is where I would say the concept we were talking about over here, where we were like building the whole thing in a server, this is where that becomes a little bit more challenging. So pretty much what someone expects to happen when they're running a CI/CD job is there's some kind of Docker container image that is the base image for what this job is going to do. And then they're kind of expecting like maybe like a VM to get magically spun up temporarily that's clean and fresh and dedicated to their job. And then it would pull down the container image that they specified in the job, and then it would run like the script that's in there. And then at the end, it would destroy itself and delete all of its like remnants. So the most obvious way you would do that is using the cloud, and you would use something maybe like a Kubernetes cluster or something like that, where you can instantiate a new Docker and container and run it and give it a bunch of access to compute resources. Because like one of the key attributes I'm going to set when I'm defining a GitHub action is like what size of machine I want it to run on and what operating system and that kind of thing. So the idea of doing all that on a single host, it's possible to do. You could have a big beefy host, and then you could give people the equivalent of like a virtual machine inside a container, and then different users who are each running an action at the same time, they could each be a different container on that computer. But really, like, it's much more likely that you would do this in a cloud context. So you would probably have some kind of farm of multiple servers that are available to run these actions on them. These are physical they're probably physical servers, really. Or they could be virtual machines, either way. But like, there's a bunch of available compute resources that are not currently in use that can be used for these jobs. And then this CI/CD system is going to have to like go get, instantiate one of those servers. I think that they're going to need to be, let's use a different image for this. Let's use the database kind of image. You're going to need some kind of like Docker image repository that's going to have all the Docker images in it. And if you use GitHub Actions, you know that like they provide some base containers that are like certain containers to run like a bash script or to run an NPM deployment or to run a Python deployment. Like they have containers that they provide for that. So those containers would all be stored in this image repo. But then also potentially people might be referencing containers that they have like stored out in the cloud and some other place. And those might be the ones that they want to run. So the way the CI/CD system will work is it'll like allocate a server for this event request that came in. It'll pull down some kind of image from the image repository, or maybe, like I said, it could be pulling it down from Docker Hub instead of from GitHub's own repository. And then it's going to run a container on that machine using that Docker image. And then inside that container, it'll run the job. And it has to kind of do some things, like it has to capture any kind of output that's coming to standard out when that container is running, so that it can give the user feedback in the console and say like, oh, here's the output of your job that's currently happening. That way, if the job fails, you'll see like the error message that it failed at, and you can debug it. So it's going to have to like tail the logs for the Docker container and capture those and stream them to the user in the web interface. And but basically, like, it's a machine that's running a container image that either GitHub provided or the user provided, and then it's just parsing the steps in the YAML file, and those have a very specific syntax of like, here are the arguments and the environment variables and things of that nature. And so then it can kind of run whatever the job is. Now there's certainly going to be some other components to this, like when you're running this container image, you're probably going to need to have access to like a token to access some system or whatever. So the container that's running on this machine will probably talk to like a secret service, and it'll have some way of like pulling a named secret that's securely stored and authenticating in order to pull the secret. So that could be like the token you need to access some API or the password for the database or whatever. But that's going to be a call out to some system. And again, the reason it's not just like doing a database query is that secret service is going to have a lot of security built into it. It's going to have to understand like whether that GitHub action actually has access to that particular secret. And so you're probably going to have this encapsulated in a separate component piece of software where things have to ask the secret service for a secret, and the secret service probably talks back to the Git brains in order to know like what you can and cannot access.
But basically, like, I guess to summarize this, is it's like event based. So whenever an event occurs, a VM it gets created, then there are like services to like, I guess, databases to take the images from, or as you said, we can directly take it from Docker Hub, and then secrets as well, I guess, is one of those key and very important aspects as well. But so essentially it could be like pub sub, right? So it's like
like the pub sub could trigger the event, and then it could pull the message from pub sub, and then it could create a VM. There's a lot of ways you could do it. Like if you were using Google products, you could use something like Google Cloud Batch, where you say like, oh, hey Batch, like make me a VM like this and run this container with this script. There's a lot of ways to do that, but that's the one component that would be a little bit hard to kind of just run on a single machine, because if anyone is going to be asking for large machines or running multiple actions at once, that would slow down the web server to the point where you couldn't actually serve like the web requests. And that's why you probably would have that on a separate cluster or a separate machine or whatever.
Makes sense.
Cool.
Yeah, I think we definitely covered a lot of things today. It's like a huge system overall, so I guess we tried to cover as many things as possible, but there's definitely like
I'll share some of these links with you. There's the GitLab overview, which is, like I said, pretty helpful and similar to what we talked about. There's a really in-depth post on the GitHub engineering blog, which I highly recommend reading. This is one of the blogs I actually, keep a close eye on, that talks all about how they made code search work. And it goes into a lot more detail than we talked about here. But like, this is just some diagram about like what it goes into building the index. And they're using Kafka, or I was saying we would probably use something like Elastic. And so this is a great read with a lot of technical details. There's also another blog post, which I will include. This is a bit older, but it basically is like how they made GitHub fast for all of these things that you could imagine when you have millions of repositories that would be very slow. So I'll share those with you so you can share them with all of your folks. And I'm going to stop sharing my screen now.
Great. But yeah, I guess thank you. Want to thank everyone who joined us, and Lucas, thank you so much for joining us as well, and for the sharing all the valuable knowledge today. Again, I'll share all the links like with the attendees afterwards, so you'll be able to dig in deeper and hopefully learn some more stuff. But yeah, then I guess have a great weekend, everyone, and we'll see you next week.
Thanks so much.
Thank you.